session chair, so I'll introduce myself. Hi, I'm Sam. Thank you all for coming this morning. I'm going to talk about lower bounds against SumOfSquares based algorithms. Can we turn down my mic a little? There's a little feedback. Thank you. Great. I'm going to talk about lower bounds against SumOfSquares based algorithms. And this talk, so my instructions from the organizers, thank you to the organizers very much for having me, by the way. My instructions for the organizers were to give a tutorial. And okay, I have to be, there's a lot of material here. This is a big area, so I have to be a little bit choosy about what I can give a tutorial on. And I decided to make it pretty basic because I think there's sort of a wide audience here, especially trying to be welcoming to folks from the crypto side of this workshop. So for folks who are SOS experts, I hope you'll bear with me for at least the first half of this talk, and maybe you can contribute some corrections or modifications or additional citations. If I'm not citing your work, it's not intentional, I promise, and I would appreciate if people tell me what I'm not up to date on. Okay, so yeah, here's the rough agenda. We're going to talk about what is this SOS thing that you might have heard about, this SumOfSquares method or SumOfSquares algorithm, and then try to situate it in the themes of the workshop, so which are, learning and high-dimensional statistics and complexity thereof, and average case complexity in service of cryptography. And then having motivated things, which will actually use a significant amount of the talk, because I want to give you a sense for what these SOS algorithms are and what they can do. Then we'll move to lower bounds. And okay, I'll talk sort of briefly about what we know, what I think is kind of the state of the art. This is an very active area. So for instance, 10 minutes ago, I just heard about a new result that I had sort of heard a little bit about, but okay, I won't quite make it into the talk. And then, where we hope to be in some years. And we'll conclude with some open problems. Okay, so what is SOS? Let's think about it purely kind of abstractly without putting it in learning or crypto contexts for starters. At heart, SumOfSquares, or SOS, is an algorithm for the following kind of decision problem. It's an algorithm that takes in a system of polynomial inequalities with real coefficients and thinking of it as having real valued variables, and asks, does this system of polynomial inequalities have a solution, right? So do P1 through PM, is there some point in Rn such that P1 through PM are all simultaneously non-negative at that point? Of course, this is an NP-hard problem, right? So if somebody comes along and tells you that they have an algorithm that solves this problem, you should ask, well, when does it work? And that will kind of be the name of the game in understanding SOS, is to understand for what kind of polynomial systems does SOS do a good job of deciding this. We'll say a little bit more in a moment about what it can really do. But before getting any deeper, why would you be interested in this problem in the first place? What makes it special among the range of NP-hard problems you might try to come up with some kind of methods to address? Well, polynomials are just an extremely expressive mathematical language, and that shouldn't be surprising to people in either statistics or cryptography. Because polynomials can talk about so many different things, it means that if you have that the SumOfSquares algorithm can be used to address algorithmic problems in an incredibly wide range of areas. So it's been a tremendous success in combinatorial optimization because polynomials can talk about graphs and tours and sets and all that kind of stuff. It actually has its origins in robotics and optimal control, where it's used to design and understand Lyapunov functions, so potential functions that can govern the behavior of a dynamical system. It's very useful in quantum information. It's turned out to have applications, actually a huge number of applications in algorithm design for high-dimensional statistics and average case algorithms. And it's turned out to actually have applications in building attacks against candidate crypto systems. So these two things I will discuss more later in the talk. Of course, this is only a subset of the kinds of things that SOS can do, but this is just to convince you, why should you care about polynomials? It's because polynomials can talk about just about anything. Okay, so back to SOS. In the next few slides, I'm going to try to give you a picture at a more concrete level of what is SOS doing when it tries to decide whether or not P1 through PM can be simultaneously non-negative over Rn. And the key concept that we need is called a SumOfSquares proof. Okay, so let's think about for a second, if I gave you this polynomial system, and I also gave you some kind of a proof, let's think first about a proof that the system can be simultaneously solved. Well, that kind of proof could be very simple. I could just give you the point x that does it, right? So there's short witnesses of solvability. But what about short witnesses of unsatisfiability? Do those exist? Well, what could they even look like? A sum of squares proof is one kind of way that a short or a small witness of unsatisfiability of a system could look. It's the following thing. It consists of a bunch of other polynomials. I'm going to call them Qs, one Q for every subset of the equations. Okay? And all of these polynomials, they should be sums of squares of other polynomials. Okay? That means in particular, because everything we're doing is over the reals, that all of these polynomials are everywhere non-negative, because squares are non-negative over reals. The property that this set of polynomials should have is the following identity of polynomials. So the coefficients of this polynomial in x should be all equal to the coefficients of this polynomial in x. That's the constant polynomial called -1. And the identity is that if I sum up over all the subsets, and I multiply the SOS polynomial corresponding to that subset to the product of the constraint polynomials, is what I'll start calling these, in that subset, that sum is -1. So why should this convince you, if I show you these guys, why should it convince you that this system is not satisfiable? Well, suppose it were, suppose there was an x that satisfied it, then these products would all be non-negative at that x. These guys are everywhere non-negative. So I would have a non-negative number equal to -1, and that's impossible. Furthermore, if I show you the Qs, then by just computing out these products and looking at the coefficients, you can check whether this polynomial identity holds. So this is what a small witness of unsatisfiability could look like. In what sense would it be small? Well, we're going to have a measure of the complexity of this witness. It's called the degree, and it's just the maximum degree of any term in this sum. So we'll say a proof is degree d if every term in this sum is degree d as a polynomial in x. So SOS has a huge history. Actually, it goes all the way back to Hilbert's 17th problem. But there's kind of two highlights in this history that I want to mention because they're relevant to us. The first is a totally remarkable fact that comes out of 70 years of algebraic geometry or something like that. I told you this very specific form of a witness of unsatisfiability, and you might ask, well, how specific was that? Like, if I just give you some polynomial system that's not satisfiable, should I expect for it to have one of these witnesses? And the remarkable answer is yes. Every unsatisfiable system of polynomial inequalities has a sum of squares proof of unsatisfiability. So this is a deep result in algebraic geometry. From the computer science perspective, though, we want to understand the complexity of these sum of squares proofs, because it turns out the complexity of SOS proofs will correspond to running time of algorithms that we get out of them. And for this, the important foundational result is by Perillo and Lasserre, who showed that using semi-definite programming, you can decide the existence of a degree d proof in time which is polynomial in the size of this system and exponential in d. Okay? Think of them as being over the reals in many variables. But of course, any constrained set that I can describe as a low degree variety, I can build with this, right? So I can build the hypercube, for instance, by the plus minus 1 hypercube, for instance, for adding among these polynomials the constraints xi squared equals 1. Okay, so this is the foundational algorithmic results in sum of squares. And I won't talk about how you use semi-definite programming to do this. We'll work at this abstract level of polynomials. Yeah.
So is the original result in algebraic geometry contain any bound on the degree of the sum of square proof?
I think, okay, I don't know enough to tell you exactly what this result says. I think not. There are results that give you bounds on degrees under relatively mild assumptions. Like, for instance, you can say, well, mild from a computer science perspective. For instance, if I say that the hypercube is among these constraints, like I have for every variable I that xi squared equals 1, then the degree is at most n, where n is the number of variables. I can prove anything true in degree n. And there are similar results for the sphere. Like if I have a norm of x squared is 1, then you can't prove exact, but you can get like additive approximations to the truth somehow. So in the kind of settings that we use in computer science, the right way to think of it is that once you get up to degree, which is linear in the number of variables, you can probably prove everything you want.
But for the sphere, though, I don't think we know a linear degree so far. Right? We only know cubic bound, I think.
What about this Doherty Varner thing?
I thought they don't prove linear.
Okay.
That's what I was referring to. Yeah.
I see. Okay. We should investigate offline. The high level picture is that when you make some assumptions, you can get some quantitative degree bounds. Under no assumptions, there just shouldn't be degree bounds. Like it should be arbitrarily bad. Okay, so all this means that what we get is some kind of very nice proving power versus running time trade-off, right? If I want to know something about a polynomial system, the harder the system is, I might need to spend more time, but there is always some amount of time that I can spend in order to learn whether the system is satisfiable or not. But for computer science, what we really care about is what happens at, what we can do in polynomial time, or maybe between polynomial and exponential or something like that. So what can we do with low degree sum of squares proofs that correspond to polynomial time algorithms? What's really remarkable is that this one algorithm checking whether or not a polynomial system is satisfiable seems to capture, as special cases, the best available algorithms for an incredibly wide range of problems, worst case problems, average case problems, the whole gamut. So I'm going to illustrate this throughout the talk with several examples to give you a sense of the breadth of power of this algorithm. And here's a fun example from worst case, classic algorithms you learned in undergrad algorithms class. What about the min-cut algorithm, min-cut max flow, right? We know that you can find the min-cut of a graph in polynomial time. Well, SOS captures this. It turns out, and you can actually prove this using the min-cut max flow theorem, that if the minimum cut of a graph has size c, then there will be a constant degree sum of squares proof that no cut in that graph has value less than c. Okay, I didn't tell you how to encode cuts as polynomials and stuff. That's like, but then you can encode stuff as polynomials. We're all familiar with that. So SOS captures Ford Fulkerson. Something kind of more amazing is that if I change the problem from min cut to max cut, we all know that the complexity goes crazy, right? Like it becomes a very different looking problem. It's suddenly NP hard. We have approximation algorithms, not exact algorithms. And yet, even though the problem computationally looks very different, we actually know that the best available algorithms are also captured by SOS. So if the max cut of a graph has value c, we actually know that there's a degree 2 SOS proof, not that no cut has value bigger than c, because then max cut would be solved by polynomial time SOS, but that no cut has size more than c over this funny universal constant 0.878, which you might recognize from the Gomans-Williamson algorithm for max cut. So SOS is capturing the Gomans-Williamson algorithm for max cut. And in fact, this quantitative relationship is the best you can possibly hope for under the unique games conjecture. And that picture, that for this constraint satisfaction problem, SOS captures the best available algorithm subject to unique games, is not only true for max cut, it generalizes to every constraint satisfaction problem. Okay, so I hope I've convinced you that at least from some worst case algorithmic settings, SOS is capturing an incredible range of algorithms, right? This constant, the 0.878 approximation factor. Yeah. Okay, for different CSPs, you'll have different numbers, but right. Okay. So I want to move on to average case algorithms and learning in statistics. And the high level picture on the algorithmic side is that, again, SOS captures the best algorithms we know for a tremendously wide range of very basic average case problems, right? So by average case problems here, I mean problems where there's a particular distribution that God gives you on some graphs or tensors or matrices or something, and you have to do some computational problem given graphs or tensors or matrices from that distribution. So this is a bit different from like the more classical average case complexity world, dist-NP, where the distribution is a little bit more negotiable. So for instance, problems that many of us know and love planted clique, refutation of random constraint satisfaction problems, planted independent sets in sparse graphs, and more, SumOfSquares captures the best known algorithmic guarantees. And if you're not familiar with these problems, we're going to go in detail on one of them, planted clique, in a moment. But as an aside, these are all kind of classical average case problems that we've studied to death. But and for many of them, okay, the best known algorithms are captured by SumOfSquares, but you don't necessarily need SumOfSquares to design those algorithms. One of the tremendous successes of SOS in recent years has been that it's been a really good lens to translate a lot of insights from this kind of classical average case world and bring them into high dimensional statistics, a huge range of machine learning high dimensional statistics problems. So we've seen an explosion of algorithms for robust statistics, latent variable models, tensor problems, factor analysis, all kinds of things that are more familiar to statisticians. And they use a lot of new insights, but they also draw upon insights that were gained from these kind of classical settings. Okay, but this talk is not really about that, although that's what a lot of this semester is related to. Okay, still on this theme of the power of SumOfSquares, before we talk about lower bounds, I want to give an example of planted clique to give you a sense for what does a SumOfSquares algorithm really look like in these average case settings. So let's refresh ourselves about planted clique, which is one of these basic average case problems. It's easy in some cases, it's computationally hard in others, and one of the big goals is to understand when and why does it switch from easy to hard. So in planted clique, the goal is to distinguish between these two distributions on random graphs. The first is I'll give you a graph from the Erdős-Rényi distribution, GN half. And the second is I'll give you a sample from Erdős-Rényi, but I've hidden a K clique, right? So on some number of vertices K. And as long as K is much bigger than 2 times log n, this K clique will be the unique K clique in the graph. So of course, if I just did brute force search over K cliques, I would be able to find it. Just to remind ourselves, polynomial time algorithms are known for this problem as long as K is bigger than square root of n. And conjecturally, if K is much less than root n, the problem becomes computationally intractable. And if K is less than, this conjecture has a huge number of consequences. I actually failed to list the consequences for the learning side, but there are a huge number of reductions, many of them due to Guy and his collaborators, that start with planted clique and get to hardness of a tremendous range of learning problems. But just to point out that there are consequences even outside of statistics, you can construct private key cryptography under this assumption, or maybe small variant of it. But so the fact that this has so many consequences means it's important to understand what are the best algorithms here, and do we really believe that they have to break down when you go below square root of n?
I have a question.
Yeah.
When you say distinguish, what's the goal? Do you want to distinguish with constant probability, or like what kind of probability?
Good question. Okay. I mean, I think okay, the way that I think about it is constant probability, but you raise a good point that in crypto applications, we often think of much higher probability distinguishing as being what we want to rule out. And actually, you can distinguish between these distributions with advantage like 1 over polynomial in n, right? So I can do a little bit better than random guessing. If I just flip a coin, if I don't even look at the graph to try to distinguish, I'll distinguish with probability 1/2, right? But if I look at something very trivial, like the number of edges in the graph, this graph has a few more edges, and that gives me a little bit of advantage over random guessing in distinguishing these two. So yeah, there's absolutely a subtle point here about probability of distinguishing. I'm going to think about distinguishing with constant advantage as being the kind of problem I'm interested in, just for this talk. Okay, so every talk should have a proof, and this talk was a tutorial, so I thought that I would walk us through kind of carefully, how do you get from, like people say all the time, well, SOS captures this algorithm or that algorithm. I thought it would be worthwhile to spend 5 minutes really seeing how that goes. So I hope you'll forgive me for doing a proof, but I'm going to show that SOS captures this square root of n size clique algorithm for planted clique. So first of all, what do I even do to use this system, this algorithm for refuting polynomial inequalities? How do I use it to just solve this distinguishing distributions problem? Well, I've got to decide to translate this distinguishing distributions problem into a problem about refuting a polynomial system. And this is actually a little bit subtle. We're going to return to this point later. Just what polynomial system should I choose? Because it could have consequences. But in this setting, there's kind of a canonical choice that people have studied for a long time. And what it is we'll encode being a clique of size k in this given graph as a system of polynomial equations. I can simulate equations with inequalities by putting greater than and less than, right? So let's just work with equations. And then what I'm going to do, I'm going to have this system of equations. Notice that these equations define cliquehood of size k. We'll go through why they do that in a moment. And then I'll try to refute that system, right? And if SOS can refute that system, it means that there's no clique of size k in this graph because this system was unsatisfiable, and any satisfying solution to the system would have been a clique. So why is this define cliques? Well, I have n variables, one for every node in the graph. This constraint says those variables have to take 0, 1 values, so they're an indicator vector for a subset of vertices. These variables say that for every edge in the graph, for every non-edge in the graph, either the left endpoint or the right endpoint takes the value 0, so you can't have a non-edge in your clique. And this says that there are k vertices in the clique. Okay, so the algorithm will be take the graph, write down these equations, feed it to the SOS algorithm, and ask for a proof of unsatisfiability. Okay, so this is the only slide with math in this talk, but I thought I would show you, how does it really go? And if you want to let your eyes glaze over for a couple minutes, I won't be offended. So what I'm going to show, so it's a fact that a degree D proof of unsatisfiability exists when the clique size is like square root of n over 2 to the d. And this gives you the best running time versus clique size trade-off that we know of. And this is all with high probability over a randomly chosen graph from G n half. So, how does this really go? Well, what we have to do is construct that proof, right? Which means that I need to be able to write -1 as sum of polynomials that are supposed to be non-negative if I had a clique. So let me just sort of show how this would go. And it's a little bit of symbolic manipulation, but the goal is to basically pull out polynomials from, take some simple starting points and rewrite and rewrite and rewrite until we get a bunch of polynomials that are supposed to be 0 according to our constraints. Okay, so what would I do? Here's a first fact. If I start with k squared, which is the size of the clique, eventually I want an upper bound on this quantity. I'm going to rewrite it in some funny way. Start with k squared. Well, according to this constraint, that's going to be equal to the sum of the xi's squared, which if I expand this polynomial is equal to the sum over all pairs, xi, xj. And now I'm going to split up the sum over all pairs, xi, xj, into the edges and the non-edges. And now, because of this constraint, I'm allowed to freely add and subtract edges and non-edges. Okay, so this allows me to just freely add and subtract edges and non-edges. And that means that eventually I can write k squared as the quadratic form of x at a centered adjacency matrix for this graph, plus some stuff which is supposed to be 0 according to my constraints.
There should be a factor 2 for the pink stuff, right?
Yeah, probably I'm missing a factor of 2. Thanks. Good catch. You're saying centered because the centered adjacency matrix should have like halves, like plus half minus half.
When you added and subtracted, so you had all pairs, and I think.
Oh yes. I have a 2 here. Yeah, good point. Okay, so I'm missing a 2. Thank you, Pravesh. So now I can do some additional rewriting on this centered adjacency matrix. I'm going to use the fact that a random plus minus 1 matrix has maximum eigenvalue that scales like root n, and I'm probably missing another constant here. To use an eigenvalue like a spectral decomposition of root n times the identity matrix minus this adjacency matrix, that'll be a PSD matrix. quadratic forms of PSD matrices are sums of squares. So I can do another rewrite step where I take this quadratic form and I write it in this sum of squares form. So I picked up a sum of squares polynomial and I picked up the norm of x. Oh, this doesn't quite look right, but I think it's just because I'm presenting live. Anyway, let me not go in too much detail. I think I'm overloaded on the detail on this slide, but the point is by doing more of these constraint rewrites, we can arrive at a situation where if I add up 1 and 2, I'll end up with something that looks like this. And this is what we should focus on for now. I'm going to get some number that I can control by messing around with k is equal to some sum of squares that I got out of the spectral decomposition of the adjacency matrix plus pink stuff. And pink stuff is all supposed to be 0, right? Now the last thing to check is that I can make this number be -1, and I will have succeeded in writing -1 as equal to is in this special SOS proof form. Why is this the special SOS proof form? Well, what I had to do was sum up my constraints times some polynomials. And look, these are all, pink stuff was all constraints. So all we have to do is check that we can get -1 here, but this is root n times k minus k squared. So if k is bigger than root n, I can make this side negative. Okay, thank you all for your patience. So this is how SOS is able to capture this famous spectral algorithm for planted Clique. Okay, I have one more algorithmic example, and then I'm going to finally turn to lower bounds. And this is not going to be in any detail, but since we talked about average case algorithms, and the workshop is about connections to cryptography, let me mention that SOS has had applications algorithmically as a way to stress test crypto systems, a way to stress test new assumptions in cryptography. So there's this recent breakthrough construction of indistinguishability obfuscation, which is this extremely important but elusive primitive for cryptography. Before this construction, though, there were many candidate constructions, years and years of candidate constructions. And the more recent generations of those constructions, as the constructions got simpler and simpler so that they were amenable to some rigorous analysis, they basically showed that some kind of new structured pseudo-random generator implies the existence of indistinguishability obfuscation. So you need not just any old PRG, but a PRG with some special structure. And then many of these papers, they would assume that a PRG like this exists, and they would suggest some candidates for things which might be PRGs with this special structure. But it turned out that these structured PRGs, or the candidates at least that were suggested, were repeatedly broken by application of SumOfSquares algorithms, right? And this is not a knock against these constructions, because actually the insights gained from breaking the constructions, I think, eventually led to the construction which works. But it shows that you need to worry about SOS attacks if you're going to start making assumptions in crypto. Okay, so why should we do SOS lower bounds? Now I'm done talking about algorithms. What is the merit of proving impossibility results for SOS-based algorithms? Well, I would kind of say there are two views. One is kind of a conservative view. It just says, well, SOS is a powerful algorithm. I'd like to know when it does and doesn't work, so I can know when to use it, when to try to use something else, when to give up. And there's a long history in crypto of trying to rule out attacks against your crypto system from some restricted family of algorithms. Maybe you say SOS is another good family of algorithms to try to rule out attacks from. There's a grander view as well, and I'm not going to commit to either view, and you don't have to commit either if you want to prove lower bounds, because you can just do the math. But there's a grander view that says maybe we can try to use SOS as a broad lens on average case hardness, right? For a lot of these average case problems, we're missing anything like NP hardness. We're starting to have a reductions-based picture, but even that picture needs to start with an assumption of hardness of something like planted Clique, and for that, where's your evidence? Because we don't have two-way or a web of reductions yet. So maybe we can say, well, SOS is so powerful, it captures so many polynomial time algorithms that if I can rule out SOS-based algorithms for some problem, it's really good evidence that there's no algorithm for that problem in polynomial time. So I would call this the sort of SOS's optimal view. And I think it's a very nice way to think about some kinds of problems, but it's subtle what kind of problems this view could apply to. And I'm going to try to elucidate that a little bit farther in the talk. Okay, so here's where we're at. I'm going to move to what do we know? What kind of SOS lower bounds do we know about? And very, very broadly, vaguely, what are the techniques used to prove them? And then discuss, what kind of lower bounds can we hope for going forward? And then end with some open questions. And I'm running a little bit fast, actually. So if people want to discuss points, that would be delightful. Okay. So I can't survey all of known SOS lower bounds. There's too many. This is something that's been studied now for more than 20 years. But I'll focus on these kind of classical average case problems. These two are especially classical, refuting random constraint satisfaction and planted clique, and then some more modern ones. And I'm actually not going to give too much detail on any of these. I'm going to try to zoom out and say like what kind of statements are meant by saying you have an SOS lower bound for such a problem, and roughly how do you hope to prove such things. So let's return to planted clique as our example, just so that we know, people say all the time, oh, there's an SOS lower bound for planted clique. Well, what does it mean? What's the theorem statement really tell you? So remember that our algorithm for planted clique was take your graph, write down a certain polynomial system from that graph, check if SOS can refute that system. And what we want to do now is prove a theorem that says that if the clique size is much less than root n, then that algorithm doesn't work. So what we have to do is say, well, if I set the clique size to be much less than root n, then there does not exist an SOS refutation of the clique equations for that graph. And that's exactly what this theorem says. We got almost all the way there with a slightly weaker conclusion in the sense of exactly what kind of SOS proof we allowed. SOS proofs, you could make a few different definitions. We got almost all the way there in this paper in 2016, and Shuo-Peng gave a technical improvement that gets you really to this statement. So I'm happy to clarify exactly the difference in the statements offline. But I think it's nice to finally be able to say this thing about proofs instead of something a little bit subtly different. So what we can now show is indeed that statement. With high probability over a sample from G(n)½ if you take the SOS degree to be less than log n, so log n corresponds to quasi-polynomial running times, then there is no SOS refutation of this system of equations. Okay, so that very strongly says that the algorithm I described doesn't work when k is less than root n. So what are some features of this theorem that extend to many or maybe even all of the other lower bounds we know for sum of squares? Because I don't want to go stating a million theorems like this. Let's just say what are the theorems, what are the features that generalize? They go beyond polynomial time. So actually, this is one of the weaker kind of theorems, and it's because planted clique, you can't hope for lower bounds that go beyond quasi-polynomial time. But for instance, in refuting random constraint satisfaction, we know very strong lower bounds. We know lower bounds that go all the way up to exponential time, which corresponds to linear SOS degree. They basically always are lower bounds about a particular set of polynomial equations that you induce from your, let's say, distribution distinguishing problem. So if we think about, say, constraint satisfaction, there are a couple of problems available to you. If I give you a bunch of random clauses, either I could ask you to refute the existence of a solution to a whole bunch of randomly generated clauses, or I could ask you to distinguish between two distributions on sets of clauses, one where they're totally random and there's no solution, and one where I've planted a solution. These are subtly different problems. The difference is the same as this difference between distinguishing between G(n)½ and G(n)½ plus a k clique versus given G(n)½ prove to yourself that there is no k clique. Most natively, the easiest interpretation of this theorem is that it's about hardness of this latter refutation problem, right? It says SOS won't work for refuting. we often interpret it to mean hardness of the accompanying distinguishing problem, that you can't use SOS to distinguish these two distributions. And to be clear, I believe you can't use SOS to distinguish these distributions. I think they're hard. But I want to point out the subtle difference, that it's not quite about that. And we'll return to that in just a sec. But I wanted to give you a sense of how do you prove something like this? And this will be very, very 10,000-foot view. But how could you hope to rule out the existence of SOS proofs? Well, what we do is use duality. Okay, so I didn't tell you this, but SOS proofs form some kind of a convex set. And to rule out the existence of an SOS proof, you need to construct a dual object to them. And the dual objects take the following form. They're called pseudo expectations. And by the way, when you actually do algorithm design with SOS, very often you reason in the pseudo expectation point of view rather than in the SOS proof point of view. But for this talk, it was easier to talk about proofs. So suppose that I wanted to show that there's no solution, that there's no proof like this for some system of equations PJs. Well, here's what I could do. And in fact, it turns out to be also necessary to do this. I could construct a linear operator, which traditionally we write e tilde, that takes degree d polynomials and maps them to real numbers. And it has the following properties. One is it should be normalized. The e tilde applied to the constant polynomial should be 1. And the other is it should be non-negative on squares. So this is a positive semi-definiteness property of this linear operator. And in order to rule out the existence of an SOS refutation of these equations, it should have the following additional properties. It should map any polynomial times xi squared minus xi, which is this side minus this side, to 0. It should map any polynomial times this side minus this side to 0. Sorry, I have mismatch notation k versus that, but don't worry, k is supposed to be a little less than root n. And it should map any polynomial times xi, xj for non-edges ij to 0. If I could construct something like this for a fixed graph G, what I would do is I would apply this linear operator to both sides of this supposed SOS proof. And I would get on the left a negative number because it's linear and e tilde of 1 is 1. And on the right, I would get a non-negative number because these guys would all be 0 except for the empty set S. And then the empty set, this guy would be a sum of squares. So I'll get something non-negative. So if this e tilde thingy exists, it means that no SOS proof can exist. And basically all constructions, all proofs of SOS lower bounds, they construct these objects. Now, what makes this hard? Well, yeah, absolutely.
It's easy to see the other way, that if there's no proof like that, then you can construct this.
No, it's not easy. It would be easy if I had illustrated for you a bunch of convexity facts. So it's true by convex duality. It's actually only true under some mild assumptions on the PJs that make there basically be no duality gap in some underlying convex program. So if you went out and wrote these things out as convex sets, and then you applied a bunch of like theorems of the alternatives that you know, Farkash lemma and this kind of stuff, you would get this is a theorem of the alternative, right? Either one of these things exists or the other one does. But yeah, no, it's not obvious from the way that I've presented it. Okay, so what makes this hard? What makes this hard for these average case problems? Well, I want to show not a result about some fixed, let's say, graph or CSP that I can really get my hands on. I want to show something happens with high probability for a random graph or a random CSP, right? I want to show that for this random set of polynomial equations that I induced from a graph or a CSP, that there's no SOS refutation of those random equations. And for that, I need some kind of rule, like for every G, basically, or for most Gs, I need to construct one of these e tildes. So I can't really do the construction by hand, right? The construction has to be somehow symbolic in G, right? There has to be a rule that tells me how to take this graph or CSP or whatever and map it to a linear operator e tilde. And the difficulty is like, what the heck should the rule be? Like how should this linear operator depend on G? And for a lot of years, this was done in like a very ad hoc fashion. It was just not clear how you would do this. And it was a major roadblock for constructing sum of squares lower bounds beyond very low degrees. One place where this was solved early was for constraint satisfaction, where it turns out that you can do a sort of inductive construction of E tilde. But for problems beyond constraint satisfaction, this was a major sticking point. Until in 2016, we discovered this technique called pseudo calibration. And it's not going to work in the next 15 minutes for me to describe on any technical level what pseudo calibration is. But what it does is it's a canonical way to construct this map that takes as input a supposedly hard distinguishing problem. So we've got this interesting interplay between distinguishing and refutation. We're trying to prove a lower bound for a refutation problem. We need to build this, we need this technical step. And the way we're going to do it is we're going to switch to distinguishing. And if I can get a hard distinguishing problem, I can get a canonical construction of this E tilde, of this pseudo expectation. So in planted clique, we're thinking about this clique refuting problem that lives entirely in GN half. But to construct this map, we think about the distinguishing problem, GN half versus GN half plus a K clique. And we use the fact that low degree polynomials in the edges of the graph can't distinguish these two distributions. And it turns out that the fact that those low degree polynomials can't distinguish means that you can use the low degree moments of this distribution to construct a rule that maps graphs to linear operators. Okay, how do you do that? I'm not going to have time to say. But this pseudo calibration technique, okay, this is going to be a controversial slide, but I'm willing to stand up here and claim that for average case SOS lower bounds, it is or should be all powerful. Like every lower bound that we know either is proved using pseudo calibration or maybe a small variant of it. And I'm not committing to exactly how you implement this rule. So, I'm covering my ass here. Or should be provable this way. So I think we actually maybe don't know directly. I'm not sure anybody wrote down that the CSP proofs were actually pseudo calibrated. If anybody has, it's Pravesh. But
you don't really meet them, but they are.
Yeah. So sometimes you can do it in other ways, either ad hoc ways or in CSPs. They're actually very nice ways to do it by reasoning about graph expansion. But all of these lower bounds can be proved via pseudo calibration. So it seems to be a kind of universal technique for proving SOS lower bounds, except that the way you analyze it so far, this is kind of we're getting to the state of the union part of this talk. So far, we don't really know canonical analyses of pseudo calibration. So it provides you this construction of this linear operator, but it doesn't tell you how to prove that that linear operator satisfies all the properties you need it to satisfy. And thus far, we basically only know case-by-case proofs of this for particular refutation problems. And these case-by-case proofs, by the way, they are like very intense. There's like serious random matrix theory going on, random matrices with highly dependent entries with very crazy spectra. There's a bunch of very non-trivial random graph stuff going on. Like Pravesh has this paper on CSPs where they do a very detailed analysis of small subgraphs in sparse random graphs. So this is major technical lifting to prove these results, even though we think that pseudo calibration should be universal. It should sort of always work without worrying about details of the setting that you're in. This is one of the major mysteries remaining in SOS lower bounds, is why this universal technique works, even though to prove it, we are always appealing to very specific technical facts. Oh, well, that was what I just said. There's a bunch of open problems to figure out why pseudo calibration works. So this is kind of, I think, from 10,000 feet where we stand. We know a lot at this point of lower bounds for average case refutation problems. And we often have matching algorithms. Okay, I don't want to say there's not work to be done. There is actually. There are still a lot of refutation problems that we don't know how to handle. We're not very good at sparse graphs, for example. But at this point, the list is getting pretty long of refutation problems that we do understand SOS lower bounds for, and pretty tight ones. we have this canonical technique for proving these refutation lower bounds, but we still struggle to implement it. What do we hope is next?
Sorry to interrupt.
Yeah, no, not sorry, please.
Yeah, so you mentioned that you'd say something about the detection versus reputation problem.
Yeah.
Did you already say the thing you wanted to say?
No.
Oh, okay.
But I'm not going to say that much more. And actually, if we have 5 minutes at the end, I'd love to discuss it because I think it's a conceptual issue. Okay, I'm just going to list a few things that I think we don't understand well enough, and maybe some wave at some ways we might try to understand them better. So, refutation versus distinguishing problems. This is a really subtle issue. We said earlier that the canonical way to think about SOS algorithms and lower bounds is as refutation algorithms, but we often want to use the lower bounds as evidence for hardness of a distinguishing problem, especially if you take this kind of broad view, this SOS is optimal view, that an SOS lower bound is really evidence that no polynomial time algorithm solves your problem. And I'm going to point out a couple of real risks in that view, even though I think that ultimately it's a good one, but we have to be careful how we implement it. So you can't touch this and scroll it up. So just to illustrate this again with planted clique, nobody said you had to use this system of equations to distinguish, right? You could augment SOS. You could take any other polynomial. Let's say it's a polynomial in the edges of the graph and also these supposed clique indicator variables. Any other polynomial, which with high probability over a planted instance will be non-negative if I evaluate it at the planted graph and the indicator for the clique. So that means that if I give you a planted graph, like one with a k-clique, these equations will be satisfiable. And then my algorithm could be take this new augmented system of equations and feed it to the SOS algorithm and ask for a refutation. Right? And if I get one, then say, well, we weren't in the planted case, so it must have been a GN half graph. So on some level, you would think that the lower bound that we have for planted clique, it doesn't say anything about algorithms like this. So why do I believe that SOS doesn't work for this distinguishing problem? And even how could I come to grips with this whole space of algorithms that isn't really well specified because somebody has to choose this polynomial? This is a real problem. And actually, you can fool yourself if you commit too hard to a refutation problem that you associate to a distinguishing problem. So one place that this happens, it didn't make it on the slide, is in the stochastic block model. For people who haven't heard of it, I can tell you offline. But for stochastic block model, there actually seems to be a real gap between the problem of distinguishing sparse random graphs from sparse graphs with planted communities and the problem of refuting the existence in a sparse random graph of a certain sparse k-way cut. So the natural refutation problem that you associate to that distinguishing problem, it really just has a different computational complexity. And if you associated the refutation problem that you want to associate, you would prove hardness results that are too good, that suggest they rule out algorithms that we know exist. So this is bad, right? We have to really be careful what kind of refutation problems we try to solve when we solve a distinguishing problem. Okay, I want to give one more example of some work that actually addressed this, and just to point out that you really had to work hard for this. So this was by Pravesh and Sleel and Ryan O'Donnell, where they said something like the following: well, for random CSPs, there's a similar story, right? I could try to, there's refuting and there's distinguishing. And if I care about the distinguishing problem, I'm trying to distinguish a bunch of random clauses from random clauses with a planted assignment. And if the planted assignment is drawn uniformly at random from the hypercube, then it will be, a balanced vector or an almost balanced vector. So the sum of its entries will be, maybe 0 or maybe like plus minus square root of n, depending on exactly your model. And you could say, well, for distinguishing, I could just augment my SOS, the system I'm going to feed to SOS with this additional constraint and ask, can SOS use this to do refutation? Because then I would get an algorithm for distinguishing random from planted CSPs. It turns out you can't, but it's not a trivial matter actually to prove a new theorem, a new lower bound when you augment SOS with this additional constraint. So how could we hope to resolve this issue? Well, I think part of the magic of pseudo calibration is that it relates refutation and distinguishing. In particular, if you're proving your refutation lower bounds using the pseudo calibration technique, you should never fool yourself in this way, because you'll never prove a lower bound that is stronger than the sort of distinguishing hardness of the distinguishing problem that you use to prove your lower bound. I'm not sure if that quite made sense, but I can try to expand on it offline. Basically, when you do pseudo calibration, every polynomial that you could have used to augment your system will already be ruled out for free by the linear operator that pseudo calibration constructs. So if you can use pseudo calibration to prove your lower bound, you're not going to fool yourself. But pseudo calibration is really hard, and it also only seems to make sense for pretty simple problems. Problems where we are looking at random graphs with product structure on the edges, or matrices with independent entries, things like this. Please.
So I think, so in both the examples, both Planet Clique and this paper with Snell and Ryan,
Yeah.
we were working with pseudo-calibrated pseudo distributions. I think one of the major issues with pseudo calibration, even when you succeed in doing it, is that it does not help you satisfy hard constraints exactly. So it's like, every polynomial would have about the same expectation as you expect. But if you add a constraint that this polynomial should be 0 into your program, the pseudo calibrated construction does not immediately tell you, that the resulting.
Wait. If you guys had worked with a planted distribution where the planted thing was exactly balanced, then pseudo calibration should have for free satisfied this, right?
Not really, because you truncate the pseudo calibrated.
Yeah, okay. You'll truncate it but you'll lose very tiny error when you do that, right?
Well, part of the work there is really to understand how would that affect, and we managed to find a way without really doing that. But that's also not a real problem. I think that contributes about 20% of the pages in many of the.
Yes. So okay, yeah. Pravesh makes, just to translate this to higher level. I think we can emphasize the should not in quotes here. Like, you shouldn't have this problem, but implementing that technically remains challenging. We don't quite know how to do it.
Yeah, sorry, I'm a bit confused. So when you talk about refutation, there is a distribution over the randomness, and it's over the hypothesis.
Yeah.
Shouldn't the refutation algorithm be able to distinguish randomness and the end instance? So there is no.
Yes, that's right. So a refutation algorithm is stronger than a distinguishing algorithm, because it'll distinguish random instances from any graph with a K-Clique.
Right. So so I don't exactly understand what this pseudo calibration does, but doesn't in some sense have a choice about which distribution to take over the.
Yes, there is a choice. That's right.
And it's not necessarily the kind of the natural.
Well, if you choose the natural uniform distribution, what should happen is that you'll prove refutation lower bounds that reflect nicely the complexity of the distinguishing problem you chose, distinguishing the natural uniform distribution.
Misunderstanding is that in the CSP lower bounds, you do not choose the uniform distribution over the CSP, right? You choose some other distribution that gives you some kind of KYZ like that.
The literal, so the literal pattern distribution are not really uniform. You have to plan a correct pairwise uniform distribution, etc.
And is that also what happens in the Clique proofs, or is it more complicated?
In the Clique proof, I think you manage to use the natural distribution. But CSP is not the only example where you have to work with unnatural ones. There are other examples.
Let me point out another subtlety, which is what if I really wanted to study refutation with this pseudo calibration technique? If you have a problem where refutation is harder than the natural distinguishing problem you would associate, you might need to construct a different distinguishing problem, one that whose hardness really reflects that of refutation. This goes back to the stochastic block model, where Alex and collaborators have a paper where they construct a distribution on graphs that have planted k-way cuts. That distribution is not the normal stochastic block model, and it should be harder to distinguish from random graphs than just the stochastic block model. Its hardness of distinguishing should reflect the hardness of refuting k-way cuts in sparse random graphs. So yeah, there's this pretty subtle interplay between distinguishing and refutation on the one hand, choice of planted problems on the other, and carrying these like technically implementing things when you really want to prove lower bounds remains pretty challenging. Okay, I'm close to out of time, and I wanted to hit one more topic. which is about noise. So if all you want to do, remember this narrow view versus broad view from earlier about how to interpret SOS lower bounds. If you just want to know when will SOS algorithms work or not, because you wanted to know whether to use SOS or something else, then you don't need to worry about what I'm about to say. But if you want to take SOS lower bounds as evidence of hardness for all polynomial time algorithms for some class of problems, you got to be a little bit careful about what kind of problems you put into the bucket. In particular, there are SumOfSquares lower bounds for problems that are just computationally easy. The classic example of this is linear equations that can be solved by Gaussian elimination, right? I give you a bunch of linear equations. This was in 3 variables, but whatever, just a bunch of linear equations over F2. Linear degree sum of squares corresponding to exponential running times still can't refute random instances of this. But of course, Gaussian elimination can just solve them. It's very easy. There's actually another example that didn't make it onto my slides, some recent work by a bunch of folks here at CCSI of using not Gaussian elimination, but the LLL lattice algorithm to do similar things, not for linear equations, but for actually a bunch of problems from statistics. So there's scary situations like this. This looks like a real threat to this hypothesis, this SOS is optimal hypothesis. Why is this going on? Well, SOS, it's kind of inherently noise robust. I didn't really explain why this is, but it's based on convex programming. Convex sets are very stable to little perturbations. So, if you take some computational problem and you noise up everything about it, all of the bits that specify it a little bit, SOS should kind of do the same thing on a noisy instance of that problem than on a clean instance. But what that means is that if you have problems whose computational complexity inherently changes when you go from like a clean instance to a noisy instance, SOS won't capture that, right? It'll just think that problem is always hard because it's hard when you apply noise. And that's what's happening in these linear equations situation. And I think that's what's happening in this LLL situation, but I don't understand it well enough yet. So that means that if you want to use SOS as a lens for hardness writ large, you need to talk only about sort of robust or noisy problems. And this brings me to the, this is what I just said. This brings me to the last thing that I wanted to say, which is just to capture, what do we hope for in this whole program? Like I've talked about pseudo calibration, distinguishing refutation, noisiness. What would be a statement, a theorem statement that would capture a lot of these ideas? This is something I've been really interested in while I'm here at Simons, and I think this is, this program would really wrap things up for SOS lower bounds in a nice way. And then I'll conclude the talk. So there's this low degree conjecture that's been floating around that is supposedly characterizing hardness of a wide range of distribution distinguishing problems. So in particular, the low degree conjecture says something like the following. If I have 2 distributions on some n choose k coordinate hypercube, or this could be the real numbers or something, whatever. K is not the k from Clique, k is like 2 or 3, so I'm talking about graphs or tensors or something. And then this one is a product distribution, and this one satisfies some symmetry properties. And you can't distinguish these 2 distributions by looking at their low degree moments. Then conjecturally, if you add a little bit of noise to this distribution, the resulting distinguishing problem should be hard for all polynomial time algorithms. So as Prasad said earlier in the semester, the most amazing thing about this conjecture is that it still stands after like 3 years. It's just like ridiculously strong. It's 10 times stronger than p not equal np. So it should be broken by now, and it's not, which is crazy. I mean, instances of it, like we had to refine the statements. You have to be careful what you mean by noisy and so on. Alex had some work on this, but basically the conjecture stands. And I think what would be amazing evidence for it, and also would tie a bow on a lot of SOS lower bounds, would be to prove an SOS version of this conjecture. So an SOS low degree conjecture would just replace all polynomial time algorithms by constant degree sum of squares algorithms. And this you could hope to prove unconditionally. There's nothing, no complexity roadblock standing in your way. Okay, so I'll wrap up with open problems and then we'll be done. So as I said, the SOS low degree conjecture would be very cool to resolve. There are lots of appealing special cases of it, and many of these are sort of, you could view them as fleshing out the list of SOS lower bounds for concrete distinguishing problems that we still don't understand how to prove, but because they're implied by SOS low degree conjecture, you have to be able to resolve them before you can resolve the whole conjecture. One example is getting an SOS lower bound that matches the Keston-Stigum threshold for sparse random graph problems. Although I hear some recent progress on this. Another thing that I didn't mention at all was all of these classical average case problems I talked about. They were they were about distinguishing a very random looking distribution from some kind of structured distribution, like GN half versus GN half plus a K-clique. But often especially for crypto applications, but even in statistics, if you want to solve other kinds of distinguishing problems, you want to understand their complexity. Like what if I have one structured distribution versus another structured distribution? We just conceptually, I think, lack the tools right now to use this SOS lens to understand the complexity of those problems. But they're clearly going to be important problems. Another thing that we conceptually lack the tools to understand that Ayush pointed out, which is also important for crypto applications, is how to think about the success probability of these distinguishing algorithms. For crypto, you really want success probabilities that are vanishingly tiny, whereas we often think about just constant success probabilities. And then, okay, there are also lots of technical problems. One example is understanding random matrices with dependent entries. Like this shows up in all of these SOS lower bounds. You have to understand the structure of such matrices, how their spectrum behaves. And we're just in very early days of understanding how these matrices look. And if you want to make technical progress, you basically have to understand this. Okay, thank you all for your attention. Happy to discuss more. But thanks. So since we're 5 minutes over, maybe we'll go to break and I'll be around.